the conclusion for number 1A is not a subspace because a zero polynomial is not in the set. Okay. Not a subspace because zero polynomial is not in the set. Okay. So when the first property is not satisfied, so you just conclude it as not a subspace. Okay, you don't have to do the second and third condition. Okay. So in this case, if you substitute a equal to 0, you will get a squared. If you substitute a is equal to 0, you get a still not equal to 0. But in this case, you should substitute a is equal to 0 because t squared is always 1. Okay. For example, let's say you have a t squared graph. Okay. Just a simple sketch. See this. Okay, this is the y. So, when you substitute 0, you will get a. You will still get the point, but only the value at a certain point, not at all points. So when you substitute a is equal to 0, you also have this t squared, which is not 0. So this is not a subspace. Okay. So for example, here this one, let's say this is 1, this is y is equal to x squared plus 1. So this curve can move up and down, but none of these disappear into a 0 line. Okay. So you can conclude that for question 1A, this set is not a subspace because 0 polynomial is not in the set. Okay. Okay, let's say you have another question. Another example. PT is equal to AT squared, where A is a real number. Okay. So in this case, how about the 0 polynomial? Is it exist? Yes, because if A is equal to 0, then PT is equal to 0, right? So 0 polynomial exists and it's also closed under addition and scalar multiplication. Okay, so in this case, this is a subspace. Okay, for the question 1A, that is not a subspace, but in this example, this is a subspace. Okay, now look at question 1B. Number 1B, all polynomials of degree at most 3 with integers as coefficient. Polynomials. Okay, so all polynomials of degree at most 3 with integer coefficients. Okay, so step 1, check the zero vector. Okay, so zero polynomial has all coefficients equal to 0. Okay, so 0 is an integer, so zero vector exists. Okay, so number 1, check the zero vector. Okay, so equal to 0. Okay, where 0 is an integers, so 0 vector exists. Number 2, check closure under addition. So degree 3 means that ax power of 3 plus bx squared plus cx plus d. Okay, so in this case, all the coefficients are integer. The coefficient will be a, b, c and d. Okay, so if you substitute all the coefficient a, b, c and d 0, you will get all 0 vector. Okay, okay, so now check closure under addition. Integer plus integer, you will get an integer and the degree stays less or equal to 3. Okay, so integer plus integer, you will get an integer and the degree of the polynomial stay less or equal to 3. So it is closed under addition. Okay. Number 3. Condition number 3. Check closure under scalar multiplication. Okay. So in this course, scalars are real numbers. Take a polynomial in the set, okay, p x is equal to x, okay, multiply by a scalar. Get, let's say, 1/2 x, we get 1/2x, right? So the coefficient is not an integer. Not an integer. So this one, 1 over 2, or this value half, is a real number but not an integer. It's still inside this condition, right? Real number. It's a real number but it's not an integer. So you can, the scalar can be a real number but not an integer. So we can conclude that this is not a subspace because it is not closed under scalar multiplication. Not a subspace which is not closed under multiplication. Okay. So that is question number B. Okay, now look at question number 1C. Number 1C, all polynomial in Pn such that P0 is equal to 0. Okay, so understand the condition. So P0 is equal to 0 means that constant term is 0 and the polynomial looks like t squared, t power of 3, right? So the constant term is 0. So a p, for example, squared plus bt plus c. So in this case, the constant terms a, b, c is equal to 0. So now check the subspace condition. Check the condition. Number 1, check the 0 vector. Okay, pt is equal to 0. So p0 is equal to 0. So it is included, the 0 vector. Number 2, check closure under addition. So if P0 is equal to 0 and Q0 is equal to 0, then P plus Q 0 is equal to P0 plus Q0 is equal to 0. So you can see that when you add these two polynomial, you will get the same patterns as the original one. So you can conclude it is closure under addition. Okay, and then number 3, check closure under scalar multiplication. Okay, so if P0 is equal to 0, then CP0, C is a scalar, is equal to C dot 0 is equal to 0. So these polynomials also close under scalar multiplication. So you can conclude that it is a subspace. Okay. Okay, now look at question number 2. Is it clear? Any question for question number 1? A, B, C? Okay, no question. Okay, move to question number 2. Okay, look at this. Let H be the set of all vectors of the form negative 3t, 0t. Show that H is a subspace of R3. Okay, so first recognize the pattern. Okay, there is one parameter t. Okay, one parameter t, you can see here. Okay, so let's rewrite this. Rewrite negative 3t, 0t, t 301. Okay. So what you can conclude from this manipulation of the vectors? Okay, let's see. Number 2. Okay, so this is H. Okay, so whenever you see one parameter T, okay, think of span. Okay, so rewrite this, and then any set that can be written as a span of vectors is automatically a subspace. Okay, so see that any set can be written as a span of vectors okay. So the conclusion, H is equal to span of negative 301. So H is a subspace of R3. Okay, that is answer for question number 2. Now look at number 3. Number 3, okay, now you have the two terms, right? S and T. Okay, let's separate the terms with S and T. Okay, given this W, okay, do it step by step. W is equal to, okay, rewrite this S minus 5T, S plus T, 7S plus T, negative 2T. Okay, let's separate the terms with S and T. So first S, the coefficient will be 1, 1, 7, 0. Okay, and T, negative 5, 1, 1, negative 2. Okay. Okay, so now you have two parameters or two terms and two spanning vectors. Right? You have two parameters and you just write the two spanning vectors here. So you can conclude that W is equal to span UV. Okay, so this is U and this is your V. U and V. So W is a subspace of R4. Okay, R4 because there are 4 dimension. Okay, that is number 3. Let's move to number 4. Wait, mana number 4? Oh, number 4. Question number 4. Sekejap, saya nak copy sekejap. Okay, this is question number 4. Number 4A. Okay, the question asks you, is it a vector space? Okay. Okay, so when you look here, they have two terms, right? For A, you have two terms or two parameter, A and B. And for number B, you have three parameters, A, B, and C. Okay, so first you check whether you can write it in the span set. Okay, you can find the spanning set. Okay, let's separate or rewrite the vector. Or maybe you can, in this case, you can find the zero vector first. Okay, check for the zero vector first for number 4A. 4A, check the zero vector. Substitute. A is equal to B is equal to 0. So what you will get? Do you get 0? When you substitute, you will get 0 minus 2, 0 plus 5 times 0, 4 times 0 minus 0. Okay, so this is equal to negative 2, 0, 0. So this is not equal to 0. Right, so the 0 vector is not in W. You can conclude that the 0 vector is not in W. Okay. This one you cannot write in the span set. Okay. So if the 0 vector is not produced, stop immediately and just conclude that this W is not a vector space. Okay. Okay, let's look at question B. For B. Okay, this one is not about checking rules. It asks us to express W as a span. Okay. So you have 3A plus 2B, 0, A plus B plus C, and 2C minus A. Okay. So rewrite this, express this W as a span. So W is equal to A times 3, 0, 1, negative 1. Okay. B times 2, 0, 1, 0 plus C 0, 0, 1, 2. Okay. Did you get the same spanning set as me? Okay. So each parameter gives one vector. Here, 1, 1, 2, 3. So you can conclude that a spanning set is as 3, 0, 1, negative 1, 2, 0, 1, 0, and 0, 0, 1, 2. Okay. The spanning set is a set that span W. Okay. So when you can write in the spanning set, that means that it is a vector space. Okay, number 4, A and B finish. Let's move to question number 5. Number 5A. So number 5A. Okay, let's check quickly the three conditions. Zero matrix. Okay, this is a matrix H. Matrix H. Check whether it has a zero matrix and check whether the addition keeps the same form and check whether the scalar multiplication keeps the same form. Okay. We have to preserve the structure. Okay, that's the key. Okay, so how to answer this. Number 5A. Let's check the zero vector. Okay, try to do by yourself first. Okay, look at question number 5. Check the zero vector. Check the zero matrix for this matrix H. Okay. A. Zero matrix in H. Okay. Let A is equal to B is equal to D is equal to 0. Okay. So you will get 0, 0, 0, 0. Okay. This is the element of H. So the zero matrix pass. Okay. This is for number 1 question. Okay, next you have to check the whether it is closed under addition. So how to check it? You have to let it become A and B. Okay, so let H become, let A is equal to what? A1, B1, 0, D1, and B is equal to A2, B2, 0, D2. Okay, both of these are the element of H. Okay, then A plus B is equal to A1 plus A2, B1 plus B2, 0, D1 plus D2. Okay, so this is also the element of H. So you can see that the it preserves the same structure like the original one. So it is pass, it is closed under matrix addition. So number 3, close under scalar multiplication. Okay, let's see become any scalar that is a real number and A is the element of H. Then CA is equal to C times AB 0D. This is equal to CA 0, CB, CD. This is also an element of H. So it also pass the third condition, which is close under scalar multiplication. So since H contains the zero matrix and is close under additions and scalar multiplication, H is a subspace of matrix 2 by 2. H is a subspace of matrix 2 by 2. Okay. Okay, next, the last question, number 5B. Okay, number 5B. Okay, F is a fixed 3 by 2 matrix from the question. Okay, so let's simplify this. F is a fixed 3 by 2 matrix. And then define H is an element of A, where A is a matrix 2 by 4. And FA is equal to 0. Where 0 is a zero matrix in 3 by 4. Determine if H is a subspace of matrix 2 by 4. Okay, so now let's check the three conditions. Number 1, zero matrix in H. Okay, so take A is equal to 0, the 2 by 4 matrix. Zero matrix. Okay, then F0 is equal to 0. Okay, so pass the first condition. Number 2, under addition. Okay, is it close under addition? Okay, so let A and B is an element of matrix H. Okay. Let A be element of H. Okay, so that means FA is equal to 0 and FB is equal to 0. Then we will use the distributive property of matrix multiplication. FA plus B is equal to FA plus FB. This is equal to 0 plus 0 is equal to 0. Okay. So A plus B is also an element of H. So the second condition pass. Okay, let's look at the third condition. Looking close under scalar multiplication. Okay, let A is an element of H. So FA is equal to 0. And let C is a scalar which is a real number. Then FCA is equal to CFA is equal to C times 0. So this is equal to 0. Okay. So CA is also an element of H. So the third condition pass. So H contains the 0 matrix. Okay, write the conclusion. H contains the 0 matrix and is closed under addition and scalar multiplication. Hence, H is a subspace of matrix 2 by 4. Okay. So, write the conclusion. Okay, so we just finished discuss all 5 questions for tutorial chapter 5. So, when the question asks you to prove that it is a subspace, you have to show that all the checklist or all the 3 conditions must all be true. Okay, so the first condition is you have to show the 0 vector, and you have to show that it is closed under addition and also closed under scalar multiplication. And if you can rewrite the set as a span is a linear combination of some vectors, it is automatically a subspace. Okay, you don't have to show the 3 conditions. Okay, do you have any question before we stop our class for today? No question? Okay, if not, okay, see you next week. Okay, bye, happy holiday. Thank you for your attention.